Everyone, welcome to class 110. It is the first class of unit 11. We're going to talk about electric fields. So similar to last unit, but a new topic within that topic. So the first thing I want you to do is check out the video. I have a link to here. I'll also try to put the link in the description. In the video, there's a physics teacher. He just shows a bunch of different examples of electric fields, just helping you visualize what we're talking about. All right. After you check out that video, you're going to check out a PhET simulation. So you're going to follow this link right here and then follow some of the prompts I give you. I'll go through that with you. But the first thing you do is you go to the simulation, and I would turn on here values and grid. Okay. And the first thing it tells you to do is scatter some positive and negative charges around. Write two observations about the direction of the electric field. So let's do that. Here's a positive charge, here's a negative charge, here's another negative, here's another positive. So the two things I want, just look at it for a second, try to come up with your own observation. Hopefully you notice that the positive charges have arrows going away from it. Negative charges have arrows going toward it. What you might also notice is that the arrows start to fade as you get farther away. So make sure you get the simulation up on your own first. But actually, we're only talking about direction right now. So electric field, I'm going to call it the E field, is away from positive charges. And the electric field toward negative charges. All right. Now it says reset the screen, place one positive and one negative perfectly on top of one another. What happens to the electric field? So reset the screen. I'm going to take one positive, put it there. Maybe put my grid back up and the values, and then put my negative right over it perfectly as best I can. It's a little hard to do with, this is on a touch screen, but we'll see. So it's almost perfect. It's a little off, but what you'll notice here is that when it's just about perfect right there, just lost it, you should notice that there's no electric field when they perfectly overlap. Okay, so you could say something like they cancel each other out. Or electric field equals 0. Then it says reset the screen. Add one charge in the middle of the screen. Drag the sensor around. Write down an observation about the strength of the electric field. Okay, so let's see. Put this one away so we only have one charge. Here's the sensor, this little yellow thing. So the units for electric field, there's two different units. This is in volts per meter. Don't worry about what that is now. Just know that it's a unit. So let's see, move the sensor close, look at the electric field strength, move the sensor far away, close, far away. Okay, and also obviously it's always pointing away from the positive. So closer to charge, stronger. And maybe you also want to write farther from charge, weaker. Means the same thing, right? Just want to point something out. What do you think? How would this change if we replace that positive charge with a negative? Exactly right. The electric field is going to point towards it now. Right? The sensor's changed directions. Now it's pointing towards the negative, away from the positive, just like we saw earlier. Now again, it says reset the screen, add one positive charge, add the grid, add values, place the charge perfectly at the intersection of the vertical and horizontal major axes. See the image. Okay, so here's what I want you to do. We're going to clear the screen. Actually, well, I don't really need to clear it. I take this positive and put it as best I can right at one of those intersections. As best as I can. Okay. Something like that. And it says, place the sensor 5 boxes away from the charge. How strong is the electric field? So let's see. 5 boxes away. As best as I can. Doesn't have to be perfect, but it should be pretty close. It's about 35 volts per meter. Now place the sensor 10 boxes away from the charge. How strong is the electric field? So let's see, I'm going to move it 10 boxes away. So it's about 9 volts per meter. So if you go twice as far away, 2 times as far away, you blank the electric field strength. Let's fudge these numbers a little bit. Let's say it wasn't 35. Let's say it was exactly 36. A little easier to see. So let's see. When we doubled the distance, we went from 5 boxes to 10. We got 1/4 the electric field strength. So you quarter, or you 1/4 the electric field strength. If you cut the distance in half, so let's say you went from 10 boxes to 5, you quadruple the strength, right? If you cut the distance in half, you quadruple the field strength. Right, if you went from 10 boxes, the field strength is 9, to 5 boxes, you cut the distance in half, you quadruple the field strength. The relationship between electric field strength and distance is, and this is a little familiar, an inverse square. Leaving the sensor 10 boxes away from the charge, add a second positive charge right on top of your first. How strong is the electric field? Let's see. So if I take another positive charge and throw it right on top, so I have twice as much charge now. Looks like my electric field strength is almost exactly 18 volts per meter. So if you double the charge of your object, you double the electric field strength. If you cut the charge in half, if I were to take it away now, so going from 2 charges back down to 1, I go back to 9. So if you cut the charge in half, you cut the electric field in half. The relationship between electric field strength and this shouldn't say density, this should say charge, is linear. Some people might say direct, but we're going to say linear. So the which graph depicts the relationship between electric field strength and distance? So electric field strength and distance is the inverse square, which would be this relationship here. Okay? The relationship between electric field strength and charge is linear. So that looks something like that. All right? That would be this one here. All right, so we're going to draw some electric fields. So it says draw 8 electric field lines around each of the 2 particles below. Direction of the arrows is important. So remember, electric field lines go away. We'll switch to blue. Go away from positive charges. Make sure they're as evenly spread out as you can. They don't have to be perfect, though. And they should all be roughly the same size. And electric field lines go toward negative charges. All right, something like that. So now we're going to draw how electric field lines interact. Okay, you have to draw 8 lines per pair. It's important to note that electric field lines never cross. All right, so really common misconception here. Let's say this middle one here, the 2 positive charges. A lot of people think, okay, electric field lines go like this. This would never happen. Okay, they can't cross into each other. That just won't work. So let's look at what happens. So positive, negative one, we're starting on the left. So away from positive toward negative, away from positive toward negative. What they actually do is they kind of like curve, sort of like this. You might get one like this out here. There's really an infinite number of lines, but for our purposes, we can't really draw that many. How many do I have here? 5. So we'll draw another one in there, another one there, another one there. I think that's the right number. And then we have some going out here. All right. Now what goes on with these that are the same? So this stuff out here doesn't really change. So these are going away. These are going away, 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 and away. But what goes on in between? Well, this is where it gets a little bit interesting. This one we could kind of draw straight up. This we could draw straight down. Again, going away from the positives. But in between, what happens? Something kind of like this happens. The lines kind of like, I guess your math teacher could say they create like an asymptote. Something like that. I think I only draw 7 there, but that's fine. All right, and those lines never cross. Okay, if you were to draw those arrows and extend them, that they would never cross. If you had to guess, what would the negative one look like? So again, this stuff, doesn't really change too much. Lines go toward it. Then here we have those curved lines, something like that. All right. So the electric field is weaker. Yeah, we said that last class, right? Or last page, weaker the farther you are away, which is intuitive. Now, this next one's a little bit tricky. It says draw the electric field line between two charged plates. What does that look like? It actually looks something like this. Well, away from positive toward negative. Okay, so you could guess what it looks like. So if we draw that, but at the edges it kind of like bows out, something like that. Now you might be saying, well, what about the electric field here, 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 electric field here, here, here? There is some there, but for various reasons that actually ends up canceling out as you get pretty far away from it. As you get really far away from these things, the positive and the negative end up canceling each other out. Like if you're like all the way over here, let's say, like way down here, let's say you're like 10 miles away and you're all the way down here at this point. Okay, the positive here and the negative here will actually effectively, once you're really far away from the plates, be the same distance away, right? If like one's a million miles away and the other one's a million miles plus 1 foot away, they're basically the same distance away. So they end up canceling each other out at that point. But don't worry about that too much. Just focus on between the plates. So a really important idea is that the electric field strength between plates is the same everywhere. What does that mean? Well, let's take 3 points, A, B, and C. Okay, as long as you're not touching, let's forget about touching the plates. A, B, and C are all, one's closer, A is closer to the positive, C is closer to the negative, B is right in between. They all have the same strength. The electric field is the exact same at A, B, and C. Okay, it's no different. But it's important to note that the farther apart the plates are, the weaker the field. All right. So electric field rules. Electric field lines point away from positive charges and toward negative charges. Electric field lines never cross. Electric field lines always intersect the surface at right angles. Now, I didn't really make a point of that. I should have said that a little bit better. But where an electric field line meets a surface, it hits it perpendicularly. Like if you really focus in, like let's say right here, these are like right angles right there. Like that's a right angle, that's a right angle, and so on. It's just worth noting and knowing. Okay, electric field lines won't go like this. Like it's not going to be drawn like that. That's not perpendicular to the surface of the positive charge. Stronger electric field lines, stronger electric fields have lines that are closer together. And field strength and line density decrease as you move away from the charges. Right, you have fewer lines. Lines are farther apart as you go away. So we'll kind of see that right down here. So draw a positive charge with a very strong electric field around it and a negative charge with a very weak electric field. Let's see. So a weak electric field looks something like this. Okay, only like 4 arrows maybe, right? But a much stronger field, you can draw the arrows bigger, has more lines. And I can keep going. I can keep drawing more and more lines. But what do I mean by like the line density decreases as you move away? Well, let's draw just like a little box. All right, let's see, maybe something like this. Okay, there's a little box. If I take this box and I move it right here, right next to the charge, how many lines go through that box? Looks to me like 6 lines go through that box, right? So it's dense there, you could say. If I move that same box over here, how many lines go through that box? One, maybe you could argue three. Okay, so as I move farther away, fewer lines go through the box. Okay, same box, but since the lines are denser closer to the object where the field is stronger, that's why lines represent field strength. The more lines that go through a point, the stronger it is. Don't get too hung up on that idea. This starts to get into a little bit more advanced stuff where you start involving calculus. But just to kind of give you an idea of what they mean by that, the closer you are, the more dense it is. The farther you are, the less dense it is. That's why the field strength is less dense out there. All right.